In this video, I'll work out some examples of simplifying expressions using exponent rules. I'll start by reviewing the exponent rules. The product rule says that when you multiply two expressions with the same base, you add the exponents. The quotient rule says that when you divide two expressions with the same base, you subtract the exponents. The power rule says that when you take a power to a power, you multiply the exponents. The power of zero rule says that anything to the zero power is 1 as long as the base is not 0. Since 0 to the 0 is undefined, it doesn't make sense. Negative exponents, to evaluate x to the minus n, we take the reciprocal 1 over x to the n. To evaluate a fractional exponent, like x to the 1 over n, we take the nth root of x. We can distribute an exponent over a product. A times b to the n is equal to a to the n times b to the n. And we can distribute an exponent over a quotient. A over b to the n is a to the n over b to the n. In the rest of this video, we'll use these exponent rules to simplify expressions. For our first example, we want to simplify 3 times x to the minus 2 divided by x to the fourth. There's several possible ways to proceed. For example, we could use the negative exponent rule to write x to the minus 2 as 1 over x squared. All that gets divided by x to the fourth still. Notice that we only take the reciprocal of the x squared. The 3 stays where it is, and that's because the exponent of negative 2 only applies to the x, not to the 3. Now, if we think of 3 as 3 over 1, we have a product of two fractions in our numerator. And so we evaluate that by taking the product of the numerators times the product of the denominators, which is 3 over x squared, all divided by x to the fourth. I can think of x to the fourth as x to the fourth over 1. So now I have a fraction over a fraction, which I can evaluate by multiplying by the reciprocal. That simplifies to 3 times 1 divided by x squared times x to the fourth, which is 3 over x to the sixth, using the product rule, since x squared times x to the fourth is equal to x to the 2 plus 4, or x to the 6. An alternate way of solving this problem is to start by using the quotient rule. I can rewrite this as 3 times x to the minus 2 over x to the fourth, and by the quotient rule, that's 3 times x to the minus 2 minus 4, or 3 times x to the minus 6. Now using the negative exponent rule, x to the minus 6 is 1 over x to the 6, and this product of fractions simplifies to 3 over x to the 6. The same answer I got before. The second problem can be solved in similar ways. Please pause the video and try it before going on. One way to simplify would be to use the negative exponent rule first and rewrite y to the minus 5 as 1 over y to the fifth. Thinking of this as a fraction divided by a fraction, I can multiply by the reciprocal and get 4y cubed y to the fifth over 1. By the product rule, the numerator here is 4y to the eighth, and so my final answer is just 4y to the eighth. Alternatively, I could decide to use the quotient rule first. As in the previous problem, I can write this as 4y cubed minus negative 5 by the quotient rule. And so that's 4y to the eighth, as before. I'd like to show you one more method to solve these two problems, kind of a shortcut method, before we go on. That shortcut relies on the principle that a negative exponent in the numerator corresponds to a positive exponent in the denominator. For example, the x to the negative 2 in the numerator here, after some manipulations, became an x to the positive 2 in the denominator. Furthermore, a negative exponent in the denominator is equivalent to a positive exponent in the numerator. That's what happened when we had the y to the negative 5 in the denominator and translated into a y to the positive 5 in the numerator. Sometimes people like to talk about this principle by saying that you can pass a factor across the fraction bar by switching the sign of the exponents. That is, making a positive exponent negative or a negative exponent positive. Let's see how this principle gives us a shortcut for solving these two problems. In the first problem, 3x to the minus 2 over x to the 4, we can move the negative exponent in the numerator and make it a positive exponent in the denominator. So we get 3 over x to the 4 plus 2, or x to the 6th. In the second example, for y cubed over y to the minus 5, we can change the y to the minus 5 in the denominator into a y to the 5 in the numerator and get our final answer of 4 y to the 3 plus 5, or 8. We'll use this principle again in the next problems. In this example, notice that I have y's in the numerator and in the denominator, and also z's in the numerator and in the denominator. In order to simplify, I'm going to try to get all my y's either in the numerator or the denominator, and similarly for the z's. Since I have more y's in the denominator, let me move this y to the 3 downstairs and make it a y to the negative 3. I'm using the principle here that a positive exponent in the numerator corresponds to a negative exponent in the denominator. Now, since I have a positive exponent on z in the numerator and a negative exponent in the denominator, and I want to get rid of negative exponents, I'm going to pass the z's to the numerator. A z to the minus 2 in the denominator becomes a z to the plus 2 in the numerator. Notice that my number 7 doesn't move and when I do any of these manipulations, because it doesn't have an exponent. And the exponent of negative 2, for example, only applies to the z, not to the 7. Now that I've got all my z's in the numerator and all my y's in the denominator, it's easy to clean this up using the product rule. And I have my simplified expression. In this last example, we have a complicated expression raised to a fractional power. I'm going to start by simplifying the expression inside the parentheses. I can bring all my y's downstairs and all my x's upstairs and get rid of negative exponents at the same time. In other words, I can rewrite this as 25 x to the 4th. I'll bring the y to the minus 5 downstairs and make it y to the 5th on the denominator. Bring the x to the minus 6 upstairs and make it x to the 6th in the numerator, and then I still have the y cubed on the denominator. All that's raised to the 3/2 power. Using the product rule, I can rewrite the expression on the inside of the parentheses as 25x to the 10th over y to the 8th. Recall that we're allowed to distribute an exponent across a product or across a quotient. When I distribute my 3/2 power, I get 25 to the 3/2 times x to the 10th to the 3/2 divided by y to the 8th to the 3/2. Now the power rule tells me when I have a power to a power, I get to multiply the exponents. So I can rewrite this as 25 to the 3/2 times x to the 10 times 3/2 over y to the 8 times 3/2. In other words, 25 to the 3/2 times x to the 15th over y to the 12th. Finally, I need to rewrite 25 to the 3/2. Since 3/2 can be thought of as 3 times 1/2, or as 1/2 times 3, I can write 25 to the 3/2 as 25 to the 3 times 1/2, or as 25 to the 1/2 times 3. Well, using the power rule in reverse, I can think of this as 25 cubed to the 1/2, or as 25 to the 1/2 cubed, since when I take a power to a power, I multiply the exponents. 25 cubed to the 1/2 might be hard to evaluate, since 25 cubed is a huge number. But 25 to the 1/2 is just the square root of 25. So I have the square root of 25 cubed, or 5 cubed, which is 125. Therefore, my original expression is going to be 125 x to the 15 over y to the